Okay. Hello everyone, welcome back. We're already at our third video in our series on functional analysis. Again, we're starting off with a review of measure theory. I was looking over the book a little bit more deeply, and I thought that it would also be good, once we finished with this review, to also review some complex analysis. So just to give you an idea of what's ahead, after we review measure theory, we will go ahead and switch over, discuss some complex analysis. That review should be a little bit shorter, and then we'll move on to the contents of the book. But with regards to last time, I left you off with this problem we were interested in, which is, given some sets we want, how can we construct a sigma algebra we know will contain those sets? So this entire video will be about this question. How do we construct a sigma algebra that has the sets we want in it? Before we discuss that, we need some preliminary results. And I'll start with the first one, which says that given any collection of sigma algebras over a set, the intersection of that collection is also a sigma algebra over that set. So to talk about this theorem, let X be any set. If sigma sub alpha, where alpha is in this index set A, is any collection of sigma algebras over X, then the intersection of these sigma algebras, which I will define as sigma, is itself a sigma algebra over X. So when I say any collection, that could be finite, countable, or uncountable. Literally any collection. And so today we'll start by proving this result. So let me write proof here. One thing to start off, we have an intersection here of many sets. We should probably go ahead, it would be nice to ask the question and just investigate. Is this intersection empty? Because we're intersecting a lot of objects. How do we know that these objects even have anything in common? Well, if you recall to the definition of a sigma algebra, so I'll say, by the definition of a sigma algebra, we know, assuming X is a non-empty, etc., we know that each of these is a sigma algebra. In each sigma algebra, we are given two elements. Just because it's a sigma algebra, we know that each sigma alpha, we know each sigma alpha contains two elements. We know that each sigma algebra contains the empty set and contains the set X itself. Now, what does that give us? Well, if you recall the definition, I want to, I hope, again, set theory is quite essential, and I'm not going to review set theory, but this time I just want to recall the definition of what does this intersection mean? We say that a set B, right, because these are collections of sets, so elements of this look like sets, okay? So B is an element of this intersection if and only if for all alpha in A, B is an element, oh, that should say sigma alpha, excuse me. B is an element of sigma alpha. Okay, so if I know something is in this intersection, that means in particular that B is an element of every single sigma alpha. Likewise, if I know that some set B is in every sigma alpha for every alpha in A, then it's in the intersection. Okay, so because we know that each sigma alpha contains two elements, the empty set and X, we know, so therefore, the empty set and X are elements of this intersection. Okay, so therefore this intersection is not empty. Okay, so this intersection is not empty. Now all we have to prove is that it's a sigma algebra. We've already, just by virtue of investigating this question of emptiness, we've already proven the first axiom of sigma algebras right here. So I will highlight that. First sigma algebra, call it axiom or condition. So we already get that one. Okay, now we investigate the other conditions of sigma algebras. So next we need to check, and maybe I'll use a different color. That's a nice one, green. Next, we need to check closure under complementation. Okay, and again, while we're walking through this, if you haven't seen this material before, this would be a good opportunity for you to pause the video, try to prove this yourself, and then come back and then we can compare. Okay, so to check closure under complementation, we need to first let an element A, let A, some set, be an element of the intersection, and then we need to prove its complement with respect to X is also in the intersection. So let A be an element of sigma, which is this intersection. And then going back to this definition here, so box, I suppose. We know that if A is an element of this intersection, then for all alpha in our indexing set A is an element of sigma alpha. Okay? So A is an element of sigma alpha for all alpha in A. Now we know that each sigma alpha is itself a sigma algebra over X. We're given that. So because every sigma alpha is a sigma algebra, every sigma alpha is closed under complementation with respect to X, because these are all sigma algebras over X. Okay, so therefore, each sigma alpha, because each sigma alpha contains A, each sigma alpha contains the complement of A. So alpha complement is an element of sigma alpha for all alpha in A. And then what do? We go back to our definition of being an element of the intersection. So we now have alpha complement is an element of sigma alpha for all alpha in A. Well, that means that A complement is an element of their intersection. So alpha complement is an element of the intersection, which is precisely sigma. So now we have that sigma is closed under complementation. Okay. Moving on. All we have to do now is check the last condition. I suppose I'll use blue for this one. We need to check closure under countable unions of pairwise disjoint sequences. Excuse me, we need to check closure under countable unions. Okay, so to prove this, we'll just say AN for N, 1, 2, etc. be a sequence in sigma. Now what does that mean? That means that each AN, so that means that AN is an element of sigma, which is this intersection, which means that for all, this symbol means for all alpha in A, AN is an element of sigma alpha. And this is for all n, 1, 2, 3, blah, blah, blah. Okay? Okay. So given that AN, this is a sequence in sigma, by virtue of this sequence that's in sigma, this is a sequence in every sigma alpha. Okay? So AN is also a sequence in every sigma alpha. Okay. But what do we know about each sigma alpha? They are closed under countable unions. Okay. But each sigma alpha is a sigma algebra over X. So the union, we'll say from n equals 1 to infinity of an, is an element of every sigma alpha for all alpha in A. Well, this is the definition of being an element of the intersection. So therefore, we get the union n equals 1 to infinity of an is an element of sigma, right? Because sigma is the intersection of all the sigma alpha. Okay. And this is the third sigma algebra condition. And therefore, we conclude that sigma, which is the intersection of some arbitrary connection of sigma algebras, is a sigma algebra itself over X. So therefore, the intersection of any collection of sigma algebras over a set X is itself a sigma algebra over X. And we're done. So we've now proven this theorem right here. Let X be any set if sigma alpha for alpha in A is any collection, finite, countable, uncountable, of sigma algebras over X, then the intersection of this collection is itself a sigma algebra over X. Now we're going to need this for the next result. Okie dokie. So here's our theorem for building our own custom sigma algebras. So let X be any set and cursive A be a subset of the power set of X. So A is a collection of subsets of X. Then this theorem states that there exists a smallest sigma algebra containing A, called the sigma algebra generated by A. So A here is the collection of the sets we want in our sigma algebra. Okay. Oops. A is the collection of sets we want in our sigma algebra. Okay? And this theorem is saying that not only does there exist a sigma algebra that has the collection of sets we want, but there exists a smallest sigma algebra containing the sets we want, right? Because if you think about it, there always exists a sigma algebra containing the sets we want. It's the power set, right? Given any collection of subsets of X, all of those subsets are in the power set. So we don't really get much by just saying any old sigma algebra. Sometimes we want a special sigma algebra that's kind of what is the largest sigma algebra I can have without any bloat, any more sets than necessary, that contains the collection of sets I want. That's what the sigma algebra generated by A is. It's like without all the bloat, only containing the sets that are necessary so that I have a sigma algebra. And the proof for it is very simple in light of what we just proved. I'm going to let C, cursive C, be the following collection of sigma algebras. I'm going to say C is the collection of sigma algebras sigma over X that satisfy the following condition. So sigma is a sigma algebra over X, of course. I won't write that here. Containing A, so such that A is a subset of sigma. Remember, A is a set of sets. It is a collection of sets, and sigma is a collection of sets because it's a sigma algebra. So I say A is a subset of sigma. That means every set we want, right, which is contained in our collection A, is also in sigma. Okay? So I'm going to let C be this collection of sigma algebras. And you first note C is non-empty. Why? Well, I did just say, right? We know that the power set is a sigma algebra. So given any collection of subsets of X, those subsets will be in the sigma algebra of X, right? So we at least know that the power set is an element of C. The power set is a sigma algebra, and it contains all subsets, so therefore it contains every set in A. So C is not empty. That's easy. Okay? And then if I take, I'm going to let sigma, we'll say sigma star, I'm going to define that as the intersection for every sigma in script C. I basically take the intersection of all sigma algebras in our collection C. And we know by what we just proved that this is a sigma algebra over X. Okay, so we are already almost done. We have that C is non-empty, and we have that when we intersect all of these elements here, all of these elements sigma in the collection C, we get a sigma algebra. Moreover, we know because A is a subset of sigma for every sigma in the collection, right? A is a subset. All right, cursive A. It's a subset of this intersection. So therefore, sigma star is a sigma algebra containing A. Great. So we've just built a sigma algebra containing A. But again, there's more to this theorem than just that. We want to see if this is the smallest sigma algebra containing A. So what do we mean by smallest? I'll make an interjection here. That means, we'll say, let's say lambda is the smallest sigma algebra. You know, if lambda is any sigma algebra. Lambda is called, we call it the smallest sigma algebra containing, you know, A if, and only if, given, let's say, I don't know what's a good letter, given a sigma algebra, we'll say psi containing A, we have that lambda is a subset of psi. So again, lambda is the smallest sigma algebra containing A if and only if, given any other sigma algebra, call it psi containing A, lambda is a subset of that sigma algebra. So it's the smallest with respect to taking subsets with the subset relation, right? So any other sigma algebra will be bigger than the smallest. Okay? So all we have to prove here, to prove that sigma star as we've defined it is the smallest sigma algebra, all we have to do in our proof is suppose there's some other sigma algebra containing A, and then prove that sigma star is a subset of that sigma algebra. So let's do that. We'll say let lambda be another sigma algebra containing A. Okay. We want to show, WTS means want to show, that sigma star is a subset of lambda. Okay, well this is just a set theoretic proof. So I'm going to say let B be an element of sigma star. Okay, if I can show that B is also an element of lambda, we've proven the subset relation and we're done. Okay, by definition of sigma star, then B is an element of this intersection over sigma in the collection. We're taking the intersection over sigma in the collection. Okay. Now, what is this collection? If we go back to the definition of C, this collection is of every sigma algebra containing A. But lambda is a sigma algebra containing A, right? Right. So lambda is an element of this intersection. Now, since B is an element of this intersection, that means that B is an element of every sigma in the collection. But lambda is one of those sigmas in the collection. So B is an element of lambda. And we're done, because that means, so sigma star is a subset of lambda. In particular, sigma star is the smallest sigma algebra containing A. And that completes the proof. So just to review what we've covered this lecture, if you give me any collection of sets you want, you say, I want a sigma algebra, you give me your wish list. I want open sets, closed sets, whatever. I take all those in a set A. Then by this theorem, I can generate a smallest sigma algebra containing the sets you want. This is very important in particular. So we'll say an example. Let's consider our set to be X. Let's consider our set X to be the real line. Let X be the real line. And let A be the collection of open subsets of R. Then the sigma algebra generated by A, okay, and the sigma algebra generated by A is what? It is the smallest sigma algebra containing A. So the smallest sigma algebra containing all open subsets of R is called the Borel sigma algebra of R. And you might see this written, oh, that's not it, B of R. This is a cursive script B. So that's an important example of a sigma algebra generated by open subsets. What's great about this method is that to make your own sigma algebra, you don't have to list every single element. You don't need this explicit formula. All you need, give me a collection of sets you want in your sigma algebra, and then I can prove to you the existence of a smallest sigma algebra, which is the sigma algebra generated by that set, giving you the sigma algebra that has all the sets you want, and it's the smallest. And so that's what we've learned in this lecture. The next time we meet, we'll start discussing measures for the first time. Until next time, thank you very much.